Hi guys, my name is Trevor Sullivan. I am a solutions architect with StratusGrid, and in this video, I wanted to continue our learning on the Amazon DynamoDB service as it pertains specifically to a feature called Global Secondary Indexes, or GSIs for short. Now, in the previous video to this one on the StratusGrid YouTube channel, there is a video on local secondary indexes, and we talk about what they are and how you can actually create one using the AWS SDK for Rust. And GSIs are very similar in the sense that they allow you to access your data inside of a given DynamoDB table using a different query pattern than the base table itself. Remember that the DynamoDB base table has a partition key and a sort key, also known as a hash or range key. Those are the same terms for the same concepts. And basically, what those allow you to do is specify what partition you want your data to be stored on disk with. And then the sort key is literally how each of those partitions is going to be sorted in a particular order. And as we saw with the local secondary index, it allows you to specify a different sort key. However, the partition key has to match the base table. And that is something that the global secondary index allows you to work around. When you use a global secondary index instead of an LSI, you can actually specify a new partition key and a new sort key as well. So that's one of the key differences between LSIs and GSIs. Another difference between them, which we'll take a look at over in this document here called Working with Indexes in the DynamoDB Developer Guide here. We scroll down just a little bit and take a look at this table right here, we can actually see that GSIs can actually be created at the same time that you can create a table. However, you can actually create them after the table has been created as well. If you recall from the video that I did on LSIs, you have to create an LSI when you actually create the table. After a table has been created, you don't have the option any longer to create a new LSI. Also, there is a default limit on the number of GSIs that you can have per DynamoDB table. The limit is 20 by default. However, that is a soft limit in AWS, which means that you can actually request from AWS support that they increase the number of GSIs from 20 to a larger number that you can associate with a given single Amazon DynamoDB table. Now, there's another very interesting difference here that really boils down to the consistency of the data that you're retrieving from the table. One of the primary benefits of using an LSI that we didn't talk about in the LSI video, actually, is the ability to do a strongly consistent read operation. So what that means is if you have a put item call that writes a new item into a DynamoDB table, then when you read that data back from the table, that data might not be available immediately after you call the put item call, right? And so that's called eventual consistency, where at some point there might be a small delay. At some point in the future, that data will be available for retrieval. However, if you need a guaranteed or strongly consistent read that includes every single item that's been written into the DynamoDB table up until the point of your query operation, then you can do what's called a strongly consistent read, and that feature is only available on local secondary indexes. It's not available for GSIs because GSIs only support eventual consistency. So that's something that you want to think about, not when you're creating the index, but rather when you are querying the index and retrieving data out of your DynamoDB table. Now, another very interesting difference between the LSIs and GSIs comes down to the provisioned throughput. So with LSIs, they actually consume read and write capacity units from the base table. So if you have a base table that's configured with on-demand or pay-per-request billing mode, then it's going to use that read and write capacity from that pay-per-request billing mode. However, if you have provisioned throughput on the table where you specify, I want 5 read capacity units and I want 5 write capacity units, then when you query or scan an LSI, that capacity is actually being consumed from the base table itself. There is no separate provisioned throughput for an LSI. However, if you do choose to use the provisioned throughput billing mode for GSIs and the base table table itself, then they allow you to actually specify unique read and write capacity units for each of your GSIs separately from the base table. Now, something that you'll want to note is that the billing mode, whether it's on demand or provisioned throughput, does have to match. So if the base table is set to on demand, then all of your GSIs also have to be using that same on demand billing model. But if you change it to provisioned throughput, then all of your GSIs can have the specific RCUs and WCUs that you want for each of those indexes accordingly. So those are some of the different options here. With projected attributes, this is kind of similar in the sense where you can project specific attributes into the index. However, you'll note that DynamoDB doesn't fetch any attributes from the table in this case, whereas with the LSI, you actually have the ability to fetch underlying attributes from the base table that are not projected into the index. So that's kind of a limitation on the GSI side that you'll want to take note of as well. So there are some different features when it comes to LSIs and GSIs here. One other thing is that you'll have the size restrictions on LSIs. Each partition has a limitation of 10 gigabytes or less. And with GSIs, there is no size restriction for each of those partitions. So those are just some of the main differences that we want to understand when it comes to GSIs and LSIs. So let's jump over into the AWS Management Console and actually take a look at how to create and delete GSIs and how we can configure GSIs to use a particular amount of throughput or have a certain amount of provisioned throughput associated with them. So let's head over to the console here. And as you can see, I've got this table right here that already has 4 indexes associated with it. But we're going to go to this table right here called Trevor-products. And if we explore the table items, you can see that I've got 7 different items here. I've got the P category, so product category. That is my partition key for the table itself. So if we go back to the table details and look at the partition key, the base table is using that category field or attribute as its partition key. And then the product name or P_name field there is going to be the sort key for my table here. But remember that with an LSI, I could specify a different sort key. And we took a look at how we could use isAvailable as a sort key instead of the product name. But with a GSI, we could actually create a new partition key and a new sort key as well. So imagine, for example, that maybe we want to partition our data in this isAvailable attribute right here so that we have no and yes. So if we only had those 2 values, no and yes, as the options for that particular field. It is a string field, so you could actually put whatever you want in there. But if we just intentionally restrict ourselves to using those 2 different values, then we're ultimately going to have 2 different partitions in our index if we choose that as our partition key. And then once we partition based on isAvailable, we could say, well, maybe I want to use the price here as my sort key or my range key, right? So we could actually specify in the GSI that we want to use completely different attributes. So these 2 on the left, P category and P name, are the composite primary key for the base table. But then when we create the GSI, we could say, well, I'm going to partition based off of isAvailable, and then I'm going to sort based on price. And then when your application is querying the data back from this table, you'll actually be able to say, I only want to select products that are available, and I also want to limit the range query to be products within a specific price range. So you'll want to think about if that's an access pattern that your application needs, and if it is, then you can specify a GSI that matches those requirements. So what we can do is head over to our table details again right here. And if we head back over to indexes, the indexes tab right here, you'll see I have created an LSI. And of course, that was created when I actually created the table because you can't create LSIs after you have created the base table. But we do have the button up here to create an index. And same thing here under GSIs, we have the ability to create a global secondary index. And this is very different from the LSI because with an LSI, the partition key is not prompted. It has to be the same as the base table's partition key. But in the case of a GSI, that restriction is no longer in place. So I could actually say I want to use is available as a string data type. This is one of the 3 supported data types for a attribute key. Then I can sort it based off of the price field here. And that's going to be a numeric value that we want to sort on. So now I have completely different partition and sort keys or hash and range keys for my index here. You also notice that because my table is currently configured to use the on-demand billing mode, that I don't have the option to specify read and write capacity units for this GSI, because the GSI configuration has to match the base table's configuration when it comes to the billing mode. For attribute projections right down here, we can say I want all of the attributes in the table to be accessible, or I could specify keys in addition or attributes in addition to the keys that I want to include right down here, or I can just include only the keys. So let's say that maybe I wanted to include the product name, but I don't want to include the product category. Maybe I don't care what the category is. I just want to see what the product name is. I want to know if it's available. That's our partition key. And then I also want to be able to retrieve the price. So something else you want to note is that when you create a GSI, it can actually take a few minutes here. That's something that I noticed was a little bit different between GSIs and LSIs. LSIs seem to create in a couple of seconds, and GSIs can take a little bit longer to actually create. And while the GSI is in this creation mode, it actually has a background status that's not really shown here. But basically what's happening is that the GSI is being backfilled. So we have items in the base table, and we need to backfill those items into the GSI. That's kind of like doing an initial load of data from the base table into the GSI. So now you can see if we refresh here, we should see that we have 2 indexes on the Trevor-products table. We should see it's still in the creating state right here. But then when we actually go to run a query operation right here, and you can scan if you'd like to as well, but if we do a query operation, we'll actually be able to select that index once it's finished creating, and then we'll be able to specify our is available as our partition key that we want to query on. And now we can retrieve data from the table using is available instead of basing it off of the product category. So that's the key difference here between LSIs and GSIs. So let's give this a couple more seconds to create. All right, so now you can see that our global secondary index has been created right here. And if we wanted to, we could delete that as well. Remember that you're not restricted to creating and deleting LSIs along with the base table, so that is pretty nice. Now, let's talk about the provisioned throughput for the GSIs. Remember that we said that we could actually have a separate read and write capacity unit configuration for each of the GSIs that are associated with the base table. If we head over to additional settings right here, you'll notice that our capacity mode or billing mode for the base table is currently set to on demand. So therefore, we don't have any options on this screen here to change the configuration of our provisioned throughput for the GSIs. So if we go to actions and then say edit capacity, we can actually change the capacity or billing mode for the base table to provisioned throughput. And then we can specify what our read capacity units are going to be. So we'll just do maybe 1 for here. And then we can just check this box to say, use the same value for all of the GSIs. So that way we don't have to manually go through and actually change them. But if you uncheck that, then you can actually scroll down and go through each of your GSIs. So each GSI will have its own section right here. And you can specify how many capacity units you want for reading and writing on each of those independently from the base table. So right up here, this is the base table configuration, and then down here is the individual index configuration. If we had more indexes, then they would show up here, each with their own section, just like this one right here. So what we'll do is go ahead and just save this configuration. That'll change the billing mode. And now under the additional settings screen right here, previously it was set to on demand, so we didn't have any options or we couldn't see any more settings. But now you can see the base table capacity, so its current configuration, as well as the individual GSIs down here and the read and write capacity units for each of those GSIs. So that's really nice to be able to do that, but then let's go ahead and do the queries here. So we'll do query, and then instead of selecting the base table right here, we're going to select our GSI. And I'm trying to remember which one that is. I forgot the name of it already. So let's go to indexes. And so it's the one that's not prefixed with Trevor products. All right, so we're going to say index is available price. And then we're going to go ahead and say is available. I only want to retrieve items from my product catalog that are available. So I'll set that to yes. We don't have to specify a value for the sort or range key there. So we'll just run this. And now you can see that it returned 3 items here. And of course, all of those are available. So then I can just change my partition query here to say no. And now I get all of the items that are not available in my product catalog. So this is a pretty cool ability to create a GSI that allows us to query the data in the base table using a completely different pattern than the base table is using to actually store the data. So now that we understand how to do that, let's actually talk about how to use the Rust SDK for AWS, properly known as the AWS SDK for Rust. And we're going to take a look at how to actually update an existing table and create a new GSI on an existing table. To do this, we're actually going to be calling this API call over here. So if we take a look at the Amazon DynamoDB reference right here, you can see that we've got this operation or action called update table. And this is how you can modify anything on the table. So you can modify the provisioned throughput, you can modify the GSIs by adding or deleting them, and you can also change things like DynamoDB streams settings as well. That's another topic that we'll talk about at a later point in time. But if we take a look at the inputs to this API, the update table API here, you can see that we specify our attribute definitions. And the attribute definitions that you pass in here only need to correspond to the GSI attributes. You don't have to include the attributes for the base table that are being used for the partition and sort keys. So then under the global secondary index updates section, we have the ability to create or delete or update the configuration of our GSIs. When you do a GSI update operation, all you need to do is specify the name of the existing GSI, and then you can change the read and write capacity units for that specific GSI if you are using the provisioned throughput billing mode instead of the on-demand billing mode. If you're deleting a GSI, you can just specify the name of the GSI that you want to delete on the table, and that'll go ahead and clean it up. But then if you want to create a new GSI, we have to specify the key schema, which is basically which key or which attribute are we using for our partition key and which attribute from each item are we using for our sort key. Then we specify our projection options here as well. That's where we can specify which attributes we want to include. As we previously saw, when we created the GSI, we decided to include, I think, all of them here. And then we can also specify our provisioned throughput here at creation time, again, assuming that we are actually using the provisioned throughput billing mode on the base table. And then, of course, we give it a name as well. So let's talk about how to do this using the AWS SDK for Rust. So this is the update table. Previously, we've used the create table API to create a new table and create a new table with LSIs or local secondary indexes. But in this case, we're going to use one of these existing tables, this one right here that we've been looking at, and we're going to create a second GSI with the same configuration here as the one that we just created through the console, but we're going to do it with the AWS SDK for Rust rather than the AWS Management Console. So what I'm going to do is go ahead and fire up my terminal here. We'll create a new project directory. So I'll do a cargo new, and we'll call this sgddb add GSI and hit enter. And then we'll do code sgddb add GSI. Tab complete that really quick. And that'll open up our brand new project in Visual Studio Code. And if you're curious about how to install the Rust toolchain, install the crates into your project or anything like that, we are going to talk through some of that here. But I actually have another video that talks about how to install Visual Studio Code, install the Rust Analyzer extension for Visual Studio Code, which is how we actually get auto completion and a lot of programming features right inside of our editor right here. So you want to make sure that you have VS Code installed along with the Rust Analyzer extension, and of course the Rust toolchain, which includes the cargo CLI that we just used to bootstrap our project, as well as the Rust compiler, which is rustc. All right, so for our project here, we are going to do the typical cargo add. Tokyo, that's our async runtime. We're going to do a cargo add AWS config with the feature behavior version latest. I've talked a little bit about that before, but it's basically just a way to version control the internal AWS APIs. Generally speaking, you don't have to worry about it. Just use behavior version latest there. And then we're also going to install the SDK for DynamoDB specifically. And when we do the cargo add operation, and we add those dependencies to our cargo.toml file there, those are all coming from the crates.io registry. So if you head over to crates.io, you can search for all of these right here on the crates registry. This is basically a public dumping ground for any projects that want to publish their crates or kind of modules, so to speak, for Rust projects to the developer community at large. And so AWS uses the AWS SDK prefix for all of their different crates in here. Probably have to page through here to find it, but anything that's prefixed with AWS-SDK- something else is going to be a service-specific crate for each of those services. So of course, in this case, we're using AWS-SDK- DynamoDB. All right, so now what we want to do is set our environment variables. So I've already got an access key ID and a secret access key as well. Let me go ahead and just specify those here really quick and paste in my secret access key. And then we'll set our region to US West 1, because that's where my Trevor-products table is residing. And let me just really quickly make sure that this access key ID is actually matched here. I'll just go ahead and paste it in again to make sure that it does. Perfect. All right, so now we've got our environment variables set. Those are going to allow us to authenticate to our AWS account. And now, inside of our Rust project right here, we're going to go ahead and set this to an async main function. We have to do that for AWS projects because pretty much everything is done in async. There are ways to do async without making the main function, the entry point to your application, async, but we're not going to talk about that for the time being. Also, what we're going to do inside of here is go ahead and load our configuration. So to do that, we'll load the AWS config crate. Let me just do a Rust Analyzer restart server here so that it picks up on my IntelliSense now that we've added a couple of crates to the project. And we're going to call the load from env function here, await the result, and that is going to be our SDK configuration that contains the credentials, the access key ID, the secret access key, and the AWS region. So then we'll do use AWS SDK DynamoDB as DDB for short. And then down here, we'll call the DDB and then update table operation. And everything that we do in this update table operation here is going to allow us to create the new global secondary index. So again, if we refer to the REST API documentation for the update table operation, all the different SDKs like the Rust SDK, the Go SDK, the C# SDK, the Java SDK, the Python SDK, the PowerShell SDK, all of those different SDKs for AWS are ultimately calling this REST API under the hood. So that's why referring to the REST API documentation itself, rather than referring to the Rust specific documentation, can sometimes be helpful because it just shows you the raw HTTP request that is necessary to construct these operations. And most of the language-specific methods or functions that you call are going to map pretty closely to the terminology that you see in the request parameters here. So of course, we're going to call the update table API here, and then we're going to specify our table name. So we have to specify which table we are going to be creating a GSI for, right? Because you have to create a GSI on a base table. So let's specify the table name and get that out of the way really quick. We'll do table name and then specify Trevor-products right here. And I'm going to assign the result to update result as a variable, just so that we can capture that. And then if you recall from my other videos, in the AWS SDK, you have to call this send function here in order to tell it to actually create the async future for this operation. And then with Rust, we have to await the future, which basically causes Rust to actually execute that future using the async executor, which in this case is Tokio. So the Tokio async runtime will handle invoking the code that that future points to. So this is a common paradigm that you'll see with pretty much any API call within any of the AWS service SDKs. The unique part here is what we're actually doing as far as setting up the parameters for the request in this particular case. So we're going to set the table name. We also need to specify the attribute definitions, which contain the attribute name and the attribute type. So this would be, for example, is available is a attribute that is of type string. And then our price that we also want to include as our range key is of type number. And both of those are supported for the purpose of using it as a partition or a sort key. There's a lot of other data types that are supported by DynamoDB, but only binary, number, and string are supported when you're using them as the partition or sort keys. So we do need to construct a couple of attribute definitions, which I've also done before in a couple of videos. So let's do part attr, and then we'll set this to attribute definitions, and that's going to get imported from the base SDK. Let's give the Rust Analyzer extension a second here to finish its IntelliSense. Right, so Rust Analyzer has finally calmed down here, and so now we'll create a attribute definition builder, and we're going to set the we're going to call the default function here to just get a default attribute definition. And then we're going to call the attribute name function and specify the is available. That's going to be our attribute that we use as our partition key. And then the attribute type right here is going to be scalar attribute type, and it'll be S for string. So let me put that on a couple of new lines here to make it a little bit more readable. And then we also need to call the .build function here to turn it from a builder into a result. And then we also need to unwrap the result. We need to do the same thing for the range key or the sort key, depending on what you prefer to call it. And so we'll go ahead and call this let the sort attribute be price. And then the scalar attribute type is not going to be an S for string. It's actually going to be an N for number here. All right, so let's go ahead and add those to our update table API call right down here. So what we're going to do is say dot, and then we're going to add that. And let's see, it says found create. We need to actually create a client here. So I totally forgot to create a client. So we'll go up here and say, I want to create a new client, and we're going to pass in a reference to the configuration, and we'll go ahead and assign it to a variable like ddb client, and then down here we'll call ddb client.update table. All right, so then we should get IntelliSense here for the attribute definitions. So we'll add a part attr, and we'll duplicate this down and specify sort attribute. Awesome. So now that we've got the attributes declared here, we need to go ahead and specify the part of our update table API call that's actually going to add the GSI. If you remember from the REST API documentation right here, there's this top level field called GSI updates. And then we can create, we can delete, or update. So the object model in Rust is a little bit confusing, but if we use the IntelliSense to our advantage, it'll kind of guide us through the process of constructing all of the necessary objects or data structures in order to support this operation. So we have this function here called global secondary index updates, and this is going to accept a data structure of type GSI index update. So we need to construct that somewhere up here. So let's do let GSI update equal global secondary index update, and we'll use the builder type here, and let's get a default. And then we'll say that we want to create a table. So we have create, delete, and we also have update functions on here. And those kind of all map to the create, update, delete operations right here. So we'll say I want it to create a new GSI. And then we need to pass in, let's see. So we need to pass in a create global secondary index action. So that's something else that we'll have to construct, and that will be our input for this create operation here. But then, of course, in order to turn this builder into the underlying data structure, we need to build it with the build function, and that should give us the GSI update data structure here that we can use to pass in to this right down here. So we'll go ahead and specify our GSI update variable that contains that data structure, and that should satisfy that function's input constraints. All right, so for this create here, we need to pass in a create global secondary index action data structure. So we'll go above that and say let GSI create equal, and then we'll import this builder type. We'll do a default, and then we can specify the index name. So what's the name we want to give the new index? And then we need to specify the key schema and the projection and the provisioned throughput. And those all have their own data types as well. So let's go ahead and create a new line here and say index, let's do index name. And I'll say Trevor dash products dash from Rust, just so we know that it was created through the Rust SDK. And then we're going to specify our projection here. And this is going to take a projection type. Let's do let projection equal projection builder. We'll go ahead and use a default here and then specify the projection type of all. So that'll project all attributes from the base table into the GSI. So then we'll say pass in the project variable here. And we actually have to build that builder. Let's do dot build in order to get the underlying projection type there, and that should satisfy the constraint for that input. Next, let's go ahead and specify the key schema here. So we've done this when we've created tables before and LSIs, but with the key schema, we are going to specify what our partition and range key is. So let's do part schema is equal to a key schema element. And let's just do builder here. And then we'll say default dot attribute name. And this is going to be is available. That's going to be our partition key dot key type. And then this will be a key type hash or partition key. And then we need to build that, and that'll give us a result type. So we need to unwrap that as well. So nice long calls here for all these data structure creations. So let's just kind of make it a little bit more readable here. And then we can just duplicate this and say, let the sort schema, we'll say let sort schema be the price attribute. And that's not going to be the hash, that's going to be the range key attribute. So then down here under GSI create, we're going to specify the key schema of part schema. And then we're also going to do dot key schema and specify sort schema. So now both of those have been added. And then because we have a create GSI action builder here, we also need to build that. So let's do a build operation, and then that'll be wrapped in a result here as well. That's the inferred type from the IntelliSense here. So let's just unwrap that result. All right, so now we finally have this create GSI action data structure, and we can pass that into the GSI update operation here. So let's do GSI create as our input there, and that should satisfy all of the inputs. However, we also do need to specify provisioned throughput. So if we print out any errors that we get back from the API, we'll say if the update result is an error, then we're going to go ahead and just use the print line macro here to print out the error so we can see it. So we'll say update result.error. And if we attempt to run this with a cargo run operation here, we'll let it compile for a second, and we should get an error basically saying that the provisioned throughput hasn't actually been specified. And so what we're going to probably need to do is go up to our create GSI action and include the provisioned throughput as well. All right, so it looks like we have a little build failure here, so we might need to retry this. But what we're going to do for now is to go ahead and come back to our GSI create operation right here. And we'll say dot provisioned throughput. And then you can see we've got this provisioned throughput data structure here. So let's do let throughput equal provisioned throughput builder default. We'll set read capacity units to an int 64-bit integer. We'll set that to 1, and then we'll do dot write capacity units and set that to 1 as well. And again, we have this builder construct here, which is a common pattern in the AWS SDK. So we'll build that. Now we get a result type. So we'll do dot unwrap here, and then we'll just pass in this throughput data structure into the provisioned throughput here. So let's go ahead and see what happens if we attempt to run this again. Hopefully we can fix up that build failure right here. So I'm not really sure what's going on here, but the AWS SDK for Rust is not building successfully. For some reason, the AWS SDK SSO library is not working correctly. But I do have another project right over here, which is essentially the exact same source code. So let's go ahead and actually just move my source code into that project and see if we can't bypass whatever issue we are experiencing. So we'll just take all this code here, bring it over into my other main.rs file here, go ahead and paste it in, and then we'll go ahead and do a cargo run here, and looks like we're getting a compilation error here. So let's go ahead and actually include the DDB types right up here just to make sure that we are importing all of the necessary types. Do a cargo run here. And it looks like that ran successfully. So we just must be having some kind of caching issue going on in the other project. But in any case, if we come back to the table right here and do a quick refresh, we should see the Trevor products from Rust index in the creating state. And that's because we didn't get any output here because we only are printing out any errors that come back from the API. We're not actually printing out anything if it's successful, but we know that it was successful because it didn't actually print out any errors. And so this GSI that we've just created right here was created from our Rust code. So in any case, I hope you're understanding the GSIs a lot better than you did at the beginning of this video. The GSIs are very unique because they have their own separate provisioned throughput, which we can specify. We can see that over under the additional settings right here. Each index has its own RCUs and write capacity units, unlike the on-demand provisioning mode or the LSIs where you can't specify those separately. And the global secondary indexes, one of the things that really makes them unique is that they can have separate partition keys than the base table as well. So whereas LSIs must follow the partition key of the base table, the partition key of the GSIs do not have to actually match. In any case, I encourage you to play around with GSIs, understand how they work and some of the benefits around them, practice creating them and querying them as well by using the Explore Table Items feature right here, or you can watch the video that talks about querying from Rust. We don't cover indexes in that querying video, but it should give you an idea of how to at least get started with the query operation, and then you can just add in the GSI as another parameter. In any case, I hope you learned something from this video. Thank you so much for watching, and we'll see you in the next video. Take care.